Hello, we're Group 16, and this is our piston engine stress analysis final project. Table of contents. Hello, my name is Sebastian. I'm currently studying mechanical engineering. I like to play video games and soccer with my friends for fun. My favorite food is pizza. When I graduate, I want to work in the design and manufacturing industry.
Hi, my name is Santiago Campos. I'm a third year student studying mechanical engineering. I mainly wanted to go into the aerospace field after graduation, but recently I've taken an interest in energy systems and prosthetics. And then when it comes to hobbies, I mainly just play games and watch sports with my friends.
My name's Simon Diaz. I'm a biomedical engineering major. I enjoy watching movies and TV shows, as well as swimming to stay active. My favorite hobby is cooking, and I enjoy learning new recipes and trying new foods from different cultures. And I have a great interest in medical instrumentation and vaccines, and intend to pursue a career in those fields post-graduation. This project involves the simulation-based analysis of a simplified internal combustion engine assembly in SolidWorks. The assembly includes five main parts: the piston, piston pin, connecting rod, crankshaft, and engine block. Each component undergoes various mechanical analyses, including compression, bending, buckling, torsion, and thermal loading, to evaluate stress, strain, deformation, and factor of safety under realistic conditions. The project also features a design study to assess how changes in material or geometry impact performance, and includes one advanced simulation, either thermal analysis on the piston or aerodynamic fluid flow analysis. This simulation aims to support better engine design through data-driven insights into mechanical behavior and reliability.
These are simulation settings. The study for the piston was a compression simulation. The mesh type used was a solid standard mesh. For the piston, we chose cast carbon steel as the material. The bottom face of the piston was fixed in all directions. A load of 100 Newton was placed on the top face of the piston. For the piston pin, we did a bending simulation. The mesh type used was also a solid standard mesh, as well as the material, which was cast carbon steel. Both sides of the piston spin were fixed in all directions. A load of 100 Newton was placed in the middle piece along the split line that was perpendicular to the piece. The study for the connecting rod was a compression simulation. The mesh and the material were also solid standard mesh and cast carbon steel. In the bending and buckling part, the part was laid down on its sides. For the compression, the bottom part of the connecting rod was fixed in all directions. A load of 100 Newton was placed at the top of the connecting rod.
For the bending simulation, we did a simple supported bending with the edge of the bottom of the connecting rod fixed in all directions. The edge of the top of the connecting rod was then fixed in the X and Z direction. A load of 100 newtons was placed in the middle of the connecting rod along a split line perpendicular to the part. For the buckling simulation, we did a fixed pin buckling with the bottom part of the connecting rod. The edge of the top of the connecting rod was then fixed in the X and Z direction. And then again, a load of 100 newtons was placed on the top of the part.
For the crankshaft, the study for the crankshaft was a torsion and bending simulation. The mesh type used was a solid standard mesh. For the crankshaft, we chose cast carbon steel as a material. For the right face of the part was fixed in all directions. A rotational force of 100 newtons was placed on the left face of the part along axis 1. For bending, the left face of the part was fixed on all parts. A downward face force of 100 newtons was placed on the edge of the right face.
For the steady state and transient heat transfer simulation, we used a cast carbon steel as the material. The mesh was a solid blended curvature based mesh. For the steady state simulation, a temperature of 2250 Kelvin was placed on the top surface. A heat power of 8,500 watts was also placed on the top surface. Then for the transient state simulation, an initial temperature of 293 Kelvin was applied to all the exposed surfaces. Then a temperature of 2250 Kelvin was placed on the top surface along with a heat power of 8,500 watts. The simulation ran for 400 seconds with increments of 80 seconds.
For the design study on the connecting rod, we chose to find the optimal material, so we added 7 materials: cast carbon steel, ABS plastic, titanium alloy, annealed steel, and magnesium alloy. The chosen goal was to minimize von Mises stress to find the material that experiences the least internal stress under the same loading conditions.
And now for the simulation results. For the piston compression analysis, we got a max stress of 80,990 newtons per meter squared. The max displacement was 1.667 e to the negative 5 millimeters. The max strain was 3.092 e to the negative 7. And the minimum factor of safety was 3065. For the piston pin bending analysis, we got a max stress of 2.380 e to the 6. Our max displacement was 2.357 e to the negative 4. Our max strain was 6.883 e to the negative 6. And our minimum factor of safety was 104.3. For the connecting rod, the compression analysis, we got a max stress of 1.496 e to the 6 newtons per meter squared. Our max displacement was 7.099 e to the negative 4. Our max strain was 5.428 e to the negative 6, and the minimum factor of safety was 165.9.
For the buckling of the connecting rod, we had a load factor of 6,838.6 and a critical load of 683,860 newtons. Then for the bending simulation, we had a max stress of 3.303 to the 10 to the 6th exponent Newton per meter squared. The max displacement was 0.00398 millimeters. The max strain was 1.057 e to the negative 5. And then the minimum factor of safety was 75.14.
For the crankshaft bending analysis, our maximum stress was 1.269 e to the 6th. Our max displacement was 4.220 e to the negative 3. Max strain was 5.584 e to negative 6, and our minimum factor of safety was 1.956 e to the 2. Crankshaft torsion analysis, our maximum stress was 1.163 e plus 0.5. Maximum displacement was 3.943 e to negative 4. Maximum strain was 5.117 e to negative 7, and the minimum factor of safety was 2.134 e to the 3.
Then for our thermal studies, our steady state had a max temperature of 2,252 Kelvin. And then for our transient state, with every increment increasing by 80 seconds from least to greatest, we had 520 Kelvin, 948 Kelvin, 1,162 Kelvin, 1,422 Kelvin, and then 1,625 Kelvin.
For the design study on the connecting rod, our optimal material was the ABS plastic with a stress of 2.136 e to the second power.
For the conclusion, the simulation analysis of the simplified internal combustion engine provided valuable insights for future design improvements. The piston showed high stress near the pin but low deformation, indicating strength under compression. The piston pin endured transverse loads effectively with a high factor of safety. The connecting rod resisted compression, bending, and buckling, proving structurally stable under multiple load types.
Crankshaft simulations under torsion and bending revealed stress near connection points, but maintained a high factor of safety, confirming durability. Thermal studies of the piston emphasized the need for materials that resist repeated heating cycles. Material comparisons for the connecting rod show that while ABS reduced stress, only metals like titanium and steel provided sufficient strength.
Some recommendations that we would like to give. 1, focus on stress-prone connection areas in design. 2, select materials that combine low stress and high strength. 3, include thermal analysis early in the process. And 4, simulate buckling for long, slender parts to ensure stability. These findings support safer, more efficient engine component designs. And with that, we would like to thank you for listening to our presentation.